In the last video, we learned a couple of techniques for solving trigonometric equations, but the equations that we were able to solve were very straightforward and quite simple. In order to be able to solve more complex equations, we need to be able to modify the equation so that it's in a form that we can solve using techniques we've already learned. For example, if I'm given this equation, the sine of 2a equals the cosine squared of a, then I have a couple of options, but the one that comes to mind first for me is the fact that I know a formula for the sine of 2a. So if I change this left-hand side so that it's in a different form, that may get me farther forward in solving this equation. The right-hand side is only a cosine of a. I can write this as the cosine of a all squared. So it's just a cosine of a that I'm working with. Here I have a sine of 2a. So effectively I have two different angles here. I'm not going to be able to solve this equation if I have two different angles. So let's change the left-hand side using the identity we know for sine of 2a. The sine of 2a can be written as 2 times the sine of a times the cosine of a. So all I've done is change my left-hand side so that it looks different using an identity. The right-hand side, I'm going to leave the same, cosine squared of a. Now, on the left-hand side, I have a cosine, and on the right-hand side, I have two cosines, two factors of cosine. I could factor that out, but they're on opposite sides of the equal sign. So the next thing I'm going to do here is subtract the cosine squared of a from both sides. That gives me 2 times the sine of a times the cosine of a minus the cosine squared of a equals 0. Now, if I go back up to this form of my equation here, this line right here, let me highlight it. Looking at this line right here, I could have written this using the idea that x equals the sine of a and y equals the cosine of a. That would have given me 2 times x times y equals y squared. I could do that down here too with the same substitution. I now have 2 times x times y minus y squared equals 0. Equally, there may come a time when you find you don't need to make that substitution at all. You can just see that the thing that you can factor out from this term here and this other term here is one factor of cosine, and you don't need to make the substitution. That's fine. You can make the substitution for as long as you need to, and when you no longer need to do that step, then you can just skip it. I can see that what both of these terms have in common is a cosine. So I'll factor out cosine of a, and what I'm left with is 2 times the sine of a minus the cosine of a. That still equals 0. So now I have either that the cosine of a equals 0, or that 2 times the sine of a minus the cosine of a equals 0. If the cosine of a is equal to 0, then a has to be pi over 2, or a has to be 3 pi over 2. Looking at the unit circle, the points here and here have coordinates 0, 1 and 0, -1. Both of those are cosine, sine, cosine, sine, where cosine is 0. Cosine of a is 0 at pi over 2 and at 3 pi over 2. Now, for this other one, it's not really very obvious what the solution to this might be. I still have a sine and a cosine. I can't solve this equation as it is because I can't find an angle A whose sine is some value or cosine is some value. But because these are sine and cosine, if I can find a way to combine them so that I have a ratio of sine and cosine, then I could write this as a tangent. So I'm going to add the cosine of a to both sides. So I'm kind of going back on my word here. I'm reversing a step I took earlier. And now this equation says 2 times the sine of a equals the cosine of a. If I then divide both sides by the sine of a, I get 2 equals the cotangent of a. Well, that's 1 over tangent. I'm more comfortable working with tangent, so I'd really like to flip this one over. That means I have to flip this one over as well. That gives me 1 over 2 equals the tangent of a. Now all I have to do is take the inverse tangent, and I'll get the inverse tangent of 1/2 equals the inverse tangent of tangent. That gives me A, that gives me the angle A. So the tangent inverse of 1/2 equals the tangent inverse of the tangent of A. The right-hand side is just A. Of course, that assumes that A is somewhere between negative pi over 2 and pi over 2, and I'm so used to writing those symbols with equals in them, but they do not have equals in them, not for tangent. And then the right-hand side is whatever angle has a tangent of 1/2. Well, there's no friendly angle that has a tangent of 1/2. It's not an angle that's in our chart. It's not a value that's in our table. So I'm going to have to use a calculator to figure this one out. The answer turns out to be about, in fact, let me change this to approximate. A is approximately 0.4636 radians. So now notice that I have one solution here, one solution here, and I have a third solution here, but I don't know if that's the only other solution. I don't have an exact value for this angle, but I don't really need one. I just need to find an angle whose tangent is 1/2. So I'm going to draw my coordinates. Notice that the 1/2 is positive. Tangent is positive in quadrant 1 and quadrant 3. So I'm going to have an opposite over an adjacent that's 1/2. My opposite is 1 and my adjacent is 2. That can happen in two different places. Opposite is 1, adjacent is 2. Here they're both negative, but then negative 1 divided by negative 2 is also positive 1/2. So I'm looking either for this angle or this angle. By using the calculator to find this value, I've only found this angle here. So now I need to figure out what this angle is, and the answer is that it's pi plus another angle the same size as this one here. These two yellow angles are the same size, but the actual angle that I want is all the way around here. So I have to go to pi, starting at 0, I have to go to pi, and then I have to go another, however big that angle is. So I already have this 0.4636, that's still in my calculator. So to find this angle, I'm just going to hit the plus and then second pi. And my calculator tells me that how did I get a pink pen there? Hang on a second. 3.6052 is another angle A. So there's a fourth angle that's a solution to my original equation. So I have 4 angles that will satisfy this equation, but I haven't been given any kind of instructions as to where to restrict my solutions to. So I'm going to assume, without any other evidence that I'm restricted, I'm going to assume that I need to find all the solutions. That means I can add plus 2 pi k to each of these, or I can look at the pattern and figure out where, let me draw in here. One angle is here. This is my A equals pi over 2 and A equals 3 pi over 2 solutions. So I have an angle there, right? I have one solution there at pi over 2. The next one is add pi, and I get to the next one. Add another pi, and I get to the next one. Add another pi, and so on. So I can write this as A equals pi over 2 plus 2 pi k, and A equals 3 pi over 2 plus 2 pi k, or I can just write it as A equals pi over 2 plus pi k, where k is an integer. For my other two solutions, A equals 0.4636 and A equals 3.6052, I can do the same thing. Because on my unit circle, my first angle is here at 0.4636 radians. It's actually, this angle is too big, but it doesn't matter if the angles are actually to scale, as long as the triangles that you draw in here are sufficient to guide your progress. So if we assume that this angle is 0.4636 of a radian, about half of a radian, then this angle is my first solution. My second solution is pi more radians beyond the first one. And then the third one is pi more radians beyond that, and so on. So I'm adding the same number of radians to get from solution 1 to solution 2 to solution 3, from the third one to the fourth one, fourth to the fifth, and so on forever. So I can write that pair of solutions as 0.4636 plus pi k, where k is an integer. So I have these four solutions, pi over 2, 3 pi over 2, 0.4636, and 3.6052. I could add just plus 2 pi k to each of those. That would give me my 4 lines. I would need 4 lines to write out my solution. Or if I do it this way, I have a much more elegant presentation of my answer. I only need 2 lines to capture all the solutions. If I'm asked to find only the solutions within an interval, say 0 to 2 pi, then I just need to go back and write down this list of 4 solutions. It depends on the context. It depends on whether it's an academic exercise, or whether you actually need all possible solutions, or whether you're looking for some specific solutions. It just sort of depends on the context. We don't have a context here. We've just been asked to solve a trigonometric identity. For that reason, I'd be inclined to give all solutions unless I'm specifically told that I'm only looking for solutions within a particular interval. The vast majority of what we've just done, everything you see in highlighting here, except for this first step, is actually stuff we've done before. This actually may come down to here. The first thing we had to do with this equation was put it into a form that we could solve. We've solved equations, simple equations, in the past, in the previous video, in the previous section, and once upon a time, way back in, I think it might have been Unit 2. But this equation was a little different because it wasn't ready to go. It wasn't in a form that was ready to be solved. But really, what you see in highlighted green highlight here is the only thing that's new to this video. Everything else is stuff we've already done. For that reason, I'm going to do several more examples now, but I'm not going to work them all the way through. What I'll do is give you several examples of equations that aren't quite ready to start working on and show you how to set them up so that you can solve them. Our first example is one that starts out looking like a quadratic. All we need to do is factor the left-hand side, and then we can solve it in the same way as we would solve a quadratic. On closer inspection, then we can see that this squared term here is a sine, but the non-squared term is a cosine. We can't really do these unless we can find a way to get all sines or all cosines. The good news is I know another way to write the sine squared. I can rewrite this as 2 times something else for sine squared plus 3 times the cosine of omega minus 3 equals 0. That sine squared of omega, sine squared plus cosine squared equals 1. So if I want a different way to write sine squared, let's subtract cosine squared from both sides. And I get sine squared equals 1 minus cosine squared. So I can change sine squared to 1 minus cosine squared. And if I distribute, I get 2 minus 2 cosine squared plus 3 cosine minus 3 equals 0. Collecting like terms, I have 2 constants there. I end up with negative 2 cosine squared plus 3 cosine minus 1 equals 0. Now I'm going to multiply through by negative 1, multiply both sides by negative 1, and I get 2 cosine squared omega plus 3, minus 3 cosine of omega plus 1 equals 0. And now all I have to do is substitute x for cosine of omega. Once I've done that, I'll have a quadratic. I can solve the quadratic, back substitute, and find the solutions to my trigonometric equation. So this is a case where it started out looking like a quadratic, but it wasn't quite a quadratic. It wasn't all in terms of one function. A quadratic like 2x squared plus 3y minus 3 equals 0 can't be solved for values of x or y either. This one can't be solved for values of sine or cosine. If I could change this x into a y or this y into an x, then I could solve it. If I could change this sine into a cosine or this cosine into a sine, then I can solve it. So I've changed this sine squared into 1 minus cosine squared, and now everything in my equation is cosine. Now it's ready to go. Another type of problem you might see is one in which a quadratic term appears, but also a double angle term appears. Now, the sine squared can be changed to 1 minus cosine squared, but cosine of 2x is going to introduce both sines and cosines. So I'm tempted to change this one first. I'll use an identity for the cosine of 2x to change that term, and then I'll see if I need to change the other term as well, this term on the other side. So I'm going to rewrite this as 4 times, I have something else I'm going to use for the cosine of 2x, equals 4 times the sine squared of x plus 3. Now, the cosine of 2x can be written as cosine squared minus sine squared of x, or 1 minus the sine squared of x, 2 the sine squared of x, or 2 times the cosine squared of x minus 1. 3 different ways I can write this. If I choose the cosine squared minus sine squared version, and I put that in here instead of cosine of 2x, I put cosine squared minus sine squared, then I'll have a term on the left-hand side that has a sine squared, and I'll have one term on the right-hand side that has a sine squared, but I won't be able to factor a sine squared out of this one. So that's probably not the best bet. Same thing if I use 2 cosine squared minus 1 in here. I'll have a cosine squared, and that may be slightly better than a cosine of 2x, but it's still not the same as the sine squared. This version, in this case, appears to be the best fit. If I replace cosine of 2x with 1 minus 2, I keep forgetting my 2 times the sine squared of x, then everything in my equation is in terms of sine squared. Right, I'll do a little algebra, get you started here. 4 times 1 minus 4 times 2 times the sine squared of x. At the same time, I'm going to subtract 4 times the sine squared of x from both sides. And I guess I'll subtract 3 from both sides as well. Now I can combine like terms. I have negative 12 times the sine squared of x plus 1 equals 0. Or negative 12 times the sine squared of x equals negative 1. At this point, I would multiply through by negative 1, divide both sides by 12, take the square root of both sides. At this point, I hope you can see that it's a fairly simple equation and it's ready to go. You should be able to solve it at this point. Now, there's one other type of problem that you may see, and that involves having not just a 2x in a cosine or a sine, but maybe a 3x or a 5x. We call those sine and cosine of multiple angles. And that's actually the topic of our next video.